Welcome to this session on Tetragon on OK, using eBPF, security and observability for your Kubernetes cluster, right? I'm Jeevan Joseph. I'm a product manager with the Containers and Kubernetes Services team at OCI. And I just want to throw this architecture slide up, mostly just to show how complex a typical environment can be. A cloud-native application like this can have multiple services all talking to each other, and they're all doing different things, having different levels of access, having different patterns of access. And it can be a bit much to get a handle on everything that's going on inside the cluster. And a lot can happen inside a cluster, right? So from a security perspective and from the security activity that you might want to observe, when you look at a Kubernetes cluster, there are containers being created and destroyed at scale, constantly, all the time, right? Especially if you're using HPA or cluster autoscaler or both in conjunction with each other. When you have these scale events happen, you're automatically creating new containers, you're automatically destroying existing containers when you're scaling down. A lot of processes are starting up and shutting down along with these, right? So, from a security perspective, again, understanding what these processes are, how much access do they have, what exactly are they doing? Are they affecting anything outside of the container? Understanding these can be pretty crucial, right? Again, there are files being manipulated, sometimes within the container, sometimes on the host. And again, understanding all of this flux that is happening inside your cluster is pretty key to understanding how secure your cluster is, and also identifying events that can potentially be security events and trying to mitigate those as they happen. Not a day later or a week later trying to figure out, okay, what happened. Because a lot of the existing tooling in the ecosystem is centered around monitoring and then actions based on that monitoring. And typically there is a lag from events from inside the cluster being collected, them being transported into a database, and from there some queries or alerting mechanism running, and then alerting you to a problem, and then you reacting to that problem. That's a pretty long window in most cases, right? And for most cases, that is perfectly acceptable, right? But for security, that's one of those few cases where any lag can be disastrous potentially. So we'll look at how eBPF kind of like tries to solve this problem, and then we'll see a quick demo. Again, just like file activity, and other activity, network activity is equally important, right? You want to know exactly what your containers are talking to, right? Especially external hosts. Are they opening up stuff, right? And generally for network activity, that's a well-known space for most part. So there are policies that you can, there are a lot of perimeter security that you can apply, but even then, to identify bad actors within your cluster, it would be important to understand what kind of network activity is happening inside your cluster. Okay, so let's boil down security and observability, right? I'll kind of break this into three groups of things: observing stuff, reporting on the stuff, and then preventing, proactively preventing things from happening, right? And again, we can monitor file activity, process activity, network activity, right? But again, the goal is to not go through this cycle of observation, reports, and prevention, but rather to immediately act. As we observe, can we shut it down, right? And let's think about this in a very fundamental fashion, right? So we talked about file access, network access, and processes, right? What's the one thing that's common to all of this stuff where you just can't bypass it and you absolutely need its help to do any of this stuff, and that's the Linux kernel. So we could argue that the best place to implement this type of observability and action would be to implement it right inside the Linux kernel, right? Now, that's obviously a little bit, that's easier said than done, right? Because you can't really just go and add code into the Linux kernel, but you can hook into the Linux kernel, right? So you could do stuff like LD preload, which is, again, kind of easily bypassed, but just for the completeness of the conversation. You could hook into the start of a syscall, right? So Linux basically works with this, beautiful thing or API called the syscalls, the system calls, and you can hook into that. But the main disadvantage with this is when you try to observe something at the beginning of a syscall, Linux kernel probably doesn't have all the data to fully understand the event. Or you could get data during a syscall. This is the most efficient way, but this is also a little bit hard, right? Because it involves getting inside the kernel, hooking into the actual handling of a syscall. And there are two ways to do this, like LSM or Linux security modules and eBPF. And we're going to talk mostly about eBPF, right? So what exactly is eBPF, right? So at its heart, what it does is it adds functionality that can execute from within the kernel without loading a brand new kernel module. So if we go back to that original problem that we had, right? We want to do stuff from the Linux kernel without adding code to the kernel. Well, eBPF can sort of do that. It can dynamically add new ways to handle things into the kernel space without changing the kernel code. So how this is done is there's a compiler for eBPF, and that compiler for eBPF programs can compile eBPF code into native code that is executed within the kernel space. There is a verifier for this compiler because you are loading stuff into the kernel, so it needs to be secure, and the verifier can verify that whatever eBPF program that you have written is secure and safe to run inside the kernel, right? Now, what this gives us, the advantage that this gives us, is the ability to do this type of very low level monitoring that just simply cannot be bypassed and is ultra efficient, right? Because imagine a normal agent running in user space, and every time it is trying to hook into a syscall, you're doing context switching, right? And all of that context switching adds up. You're constantly shuttling data from kernel to user space and user space to kernel, and this can add up, right? So when you're running everything from inside the kernel, none of this happens. It's ultra efficient, and you have access to low-level data structures, and it is not something that can be bypassed. You just cannot disable it. The only way to disable this would be to disable the kernel. So now let's move on to a demo, and I'm going to showcase eBPF with Tetragon. Let me get my windows in order. Okay, that looks better. Okay, so I have a couple of machines here, and before I head over there, let me also briefly touch upon the Tetragon project. Tetragon is an open source project. You can find it on GitHub, and the installation instructions are also here. It is exceedingly simple. On an OK cluster, it's just a Helm chart that you can very easily install. And once it's installed, it can start monitoring your pods, right? By using kernel level calls. Now, the one quick call out I want to make here is, since we are talking about using kernel level features, what kind of operating system you use plays an important part. Now, the demo I'm going to show you is on Oracle Linux, and Oracle Linux, starting from, I forget the exact kernel version, but after this presentation I can look it up. I've also published a blog post with the same information where I call out the exact kernel version. But the kernel version that came out around May of 2022 started including eBPF and BTF support right inside the kernel. So you want to make sure you use a kernel that is recent, more or less recent, like about a year old should be good. Like there are ways to check if eBPF has been included in the kernel. And that's what you would want to use, right? And there are a couple of other tools that I'm going to use. One is the Tetra CLI. The Tetra CLI basically looks at the events that are emitted by the Tetragon processes. And what Tetragon does is it installs and hooks into the eBPF programs that are on the machine and starts generating events. And the Tetra CLI can format these events and do other interesting stuff which we'll soon see. Okay, so enough talk. Let's go back over here and let me see if I can recall a few. So I already have Tetragon already installed on this. So let's look at the output from Tetragon. So I'm not running anything right now. Okay, so thanks. So let's see what the output from Tetragon is, right? So Tetragon is running as a daemon set on my cluster, and I'm just going to see what the output is. You're going to see, I don't have any workloads running right now, but you're going to see some output from the, like what it's collected in the past, right? So that looks like a whole lot of stuff. So let's try to format it, right? Let's take that out. Maybe we pipe it to JQ. I don't know if JQ is installed. Okay, JQ is not installed. Awesome. So the demo gods are with me. Okay, so let's not use JQ. Let's actually use the Tetra CLI, right? So what the Tetra CLI does, so I just wanted to show you the JSON output that came out from it, because if you want to ingest this into a database of your own and start processing these events on your own, you'd probably want to ingest these JSON events. But if not, you would want to use the Tetra CLI. So there's one command, get events, and the output format is compact, and that looks a whole lot nicer. And that's what's been happening with this cluster, right? So there's somebody in this container called default namespace, xwing. He's been running cat on etc password. Then, so you can see that the process is starting. He opened a file, he closed a file, the process exited, he opened it up in VI, he opened the file, read 1269 bytes, he closed the file, and so on, right? So this is the level of detail that Tetragon can give us, and this is happening inside the container, right? And this is being collected right from inside the kernel. So now let's go ahead and deploy the sample workload from Cilium. I have a handy demo script here, so let me use this. Let me also increase the font size on this a little bit. Okay. Okay. Okay, so I have a few pods created, and right away I see a bunch of stuff here, right? Because Tetragon's been monitoring this stuff, and it saw a whole bunch of stuff. Now it's annotating annotating and giving me a whole lot of information. So it's saying that, okay, there's a bunch of mounts happening, and the warning sign at the end, that's because I have a tracing policy there that tells Tetragon to identify anything that is using the Linux capability sysadmin. That's like the new root in Linux, right? So if I'm running a pod with the cap sysadmin capability, Tetragon's going to identify that, and that's right away a red flag for me that, okay, these pods are up to no good, right? Okay, so now let's maybe focus back here and also deploy a couple of tracing policies, right? So we talked about like some file open type events that we saw here. This is when a container was created. It's tracking processes, it's tracking files. Now let me see what kind of tracing policies I have here. Okay, I have, yes, the file tracing policy. Now let me apply this tracing policy. Okay, before I do that, let me try to exec into one of those containers and let's try something, right? Let's exec into one of these. Okay, so as you can see here, we can see the exec. Okay, now let's see curl. Okay, and we identified some file activity, right? So I said curl oracle.com. So it opened up openssl.cnf. It opened up etc hosts. It opened up etc result.conf. So these are the files that it touched, right? Now, what if I want to do a little bit more? So let me exit out of here and let me apply a tracing policy. So I have my Tetragon repo cloned here. Okay. So out of the box, Tetragon ships with a whole bunch of tracing policies that do various things. These are all examples. I'm going to use one of their examples to show this. So let's do okay. So I've created a tracing policy. Now let's go back and exec into our container again. Okay, now let's try that command again, curl oracle.com. Okay, we have more information this time, right? So apart from reading etc host and result.conf, it now shows me, okay, this IP just connected to this IP, right? And it sent 74 bytes, that's the HTTP request, right? So now I can see network level traffic from these pods to any destination. And again, like there are perimeter security measures that can prevent egress to dangerous hosts or whatever, right? But knowing what is the bad actor, what pod is the bad actor, what's each of my pods talking to, right? Are there outliers? Are there my pod making very infrequent requests to some unknown entity infrequently? Like this can really help me, right? And so can the other features that we have talked about, right? Like imagine a Java application, right? You would expect this Java application container to have a few processes, right? Like Java being one, right? The application is running inside it, so that it's running a JVM. So it's, Java is a process that I would expect. Now, would you expect a shell, a bash terminal to run inside your Java application container? Here we can see it very clearly, right? Like bin bash inside this X-Wing container, right? Off the bat, that's a red flag to me, right? Especially when it happens 3 o'clock in the night, right? What's a shell doing inside my application container at an unearthly hour? There's a perfectly reasonable explanation for it because there's been a production event and a very nice engineer has just exec'd into that pod to troubleshoot something, right? But apart from that, when I notice that, that's immediately a red flag. So this is where Tetragon really comes in. And if you noticed, we're not running any agents. We're not modifying our applications in any way. We're not doing anything to these machines, right? It's using built-in kernel features and the Tetragon daemon set, which is using the native features, right? So there are no additional processes or anything running here other than what the kernel itself is doing. We're just collecting metrics from there, right? So it's super efficient and it is very useful, right? Now, let's talk to the third tier that we talked about earlier, right? Can we prevent something? I mean, because that would be the real deal, right? Because we can observe a lot of stuff. I mean, knowing that a bash terminal was found inside my container 3 o'clock in the morning, 3 days later, is probably not as useful as, doing it on the day and shutting it down immediately, right? So let's see if we can do that, right? So let me exit out of here and let me quickly show a tracing policy. Okay, so I have a tracing policy that I wrote here. Okay, let's apply this tracing policy. Now what this tracing policy is trying to do is it is trying to stop somebody from writing to etc password, right? So let's try to attempt that. Let's launch our shell and let's see if we can read. Okay, sure enough, we can read. Let's open it up for edit. Because so far none of these tracing policies have said anything like stop this guy, right? We are only collecting information so far, right? Let's open it up for edit. Let me yank that. And right at the bottom, let's go paste that and say user is bad guy. Okay. Let's try to save it. And we suddenly notice on the right hand side X-Wing got a sig kill. He was automatically killed by the Tetragon tracing policy, and we can see, let's try to cat this file again, and obviously we're not able to write to it, right? So we have identified that there is a sensitive file that I don't want anybody to write to. I've configured a policy that tells the Linux kernel, do not allow anyone to write to this file, right? This is very fundamentally working. So, disabling something here is not gonna remove this capability, right? Cannot be bypassed. And let's also, before we wrap up, quickly look at the tracing policy itself, right? So tracing policies, if you, okay, should read better. Tracing policies can be a little bit dense, but again, eBPF and Tetragon and other similar tools are very much nascent. So this is going to evolve over time, right? So you'll see that, okay, I'm hooking into the fd install, the file descriptor install syscall on the kernel, right? And I'm doing some tracking for that. I'm tracking, excuse me, the sysclose, and I'm also tracking syswrite. And especially with syswrite, I'm saying if this is matched, if somebody tries to write, then send him a sig kill, right? So it's pretty simple writing it, but again, at the moment, the Tetragon project assumes that the user who's writing a policy knows their way around syscalls, which again, it's a matter of time before that curve gets smoothened out, right? So again, that's it from me today. I hope you enjoyed the demo.